5 types of nebula exist, and one is literally what your solar system looked like before the sun ignited. Here's every type, bluntly explained. Not all nebulae are the same, they share a name and almost nothing else. Some are stellar nurseries, some are stellar corpses. Some are just dust doing weird things with light. And one is technically already dead by the time you see it. Here's the frame: 10 minutes, every type. A nebula is basically a giant cloud of gas and dust floating in interstellar space. That's it. The word covers wildly different objects because astronomers named them before they understood them and the name stuck. What separates them is what's happening inside, whether stars are forming, dying, glowing, or hiding behind dust. 5 families. We go from textbook classics to the ones that shouldn't exist. Start with the familiar. First up, emission nebulae. These are exactly the ones you picture when someone says the word nebula. Giant glowing clouds of hydrogen lit up in that signature deep red glow. Here's how they actually work. You have a massive young star nearby blasting out ultraviolet radiation that slams into surrounding hydrogen gas. It rips electrons off the atoms, and when they fall back into place, they release visible light. That specific red glow in every Hubble image is called H-alpha emission, essentially a cosmic neon sign. Same physics as the neon tube in a diner window, just scaled up to a few hundred light-years across. The poster child here is the Orion Nebula. You can spot it with binoculars, 1300 light-years out. Inside it sits a cluster of newborn stars called the trapezium, doing all the ionizing. Nurseries with lights on. If you see a nebula and it's red, pink or magenta, this is exactly what you're looking at. Hot gas energized by young stars, screaming light in one very specific wavelength. But here's where it gets weird. Not every nebula makes its own light, some just borrow it. Next up, reflection nebulae, quiet, cold clouds. The nearby stars aren't hot enough to ionize the gas, so instead of emitting light, the dust scatters it. Sounds familiar? It should. This is the exact same reason the sky on Earth is blue, Rayleigh scattering, basically. Shorter wavelengths bounce off tiny particles more easily than longer ones. Blue scatters, red just passes through. Point that at a dust cloud in space and you get a nebula glowing soft, ghostly blue. Zero ionization. The classic example, the Pleiades, the Seven Sisters, a famous cluster wrapped in a wispy painted blue haze. Astronomers once thought the cluster was born inside that dust. Turns out no, it's just a cosmic drive-by. Reflection nebulae often pair with emission regions, same molecular cloud birthing hot stars one spot, scattering light another. Red and blue in the same photograph, 2 mechanisms, one single cloud. A cosmic double feature happening at once. But here's the thing, same dust, same conditions, viewed from a different angle, and it goes completely dark. Third type, dark nebulae. Cold, dense clouds of dust and molecular gas that block light instead of glowing. You don't see them because they emit light. You see them because they stand in front of something brighter. Silhouettes cut out of the Milky Way. Holes in the sky. The most famous one is Horsehead in Orion. That iconic dark shape isn't carved from nothing. It's a dense pillar of dust blocking pink emission behind. Then there's the Coalsack, a massive dark patch in the southern sky that looks like a hole punched through. Barnard 68 is another, a nearly perfectly opaque blob of cold molecular gas. Here's what makes them interesting. Dark nebulae look empty, but they're the densest, coldest, most active kind. This is where new stars form. The gas inside is around 10 degrees above absolute zero. Gravity slowly wins. Cores collapse. Protostars ignite. Basically, dark nebulae are stellar wombs. The blackest patches of sky are where the next generation is cooking. So far, everything's been about birth. Gas being lit up, dust illuminated, stars being made. Now we flip. Everything from here on is death. Type 4. Planetary nebulae. And the name is a complete lie. Nothing planetary about them. William Herschel called them that in the 1700s through his early telescope. Through that scope, they looked like fuzzy little disks, basically like planets. Terrible name, but it stuck. Here's what they actually are. A sun-like star runs out of hydrogen, swells into a red giant, gets unstable. It starts shedding its outer layers into space. Not exploding, just puffing them off gently over thousands of years. What's left in the middle is the exposed hot core of the star. A white dwarf. Blisteringly hot. It blasts ultraviolet light into the gas shell it just ejected. The shell lights up. That's a planetary nebula. Think of it as a delicate glowing bubble around a dead star's corpse. And the shapes are absolutely absurd. The ring nebula is a near-perfect smoke ring. The cat's eye looks like layered spirals inside a jellyfish. The Helix nebula stares back at you like an actual eye. It's genuinely unsettling. But here's the catch. Planetary nebulae are cosmically brief. They last around 10,000 years, maybe 20,000. Sounds like a long time, until you realize the universe is 13.8 billion years old. 10,000 years is basically a blink. So every planetary nebula you see is basically a snapshot of a star mid-funeral. This is our Sun's future. In roughly 5 billion years, the Sun swells, sheds its skin, and lights up its own planetary nebula. Whatever's left of Earth gets to sit inside it. Briefly. That's how small and medium stars die. Quietly. Big stars do not go quietly. Type 5. Supernova remnants. A star over 8 solar masses runs out. It doesn't puff. It collapses. In a fraction of a second, the core implodes, outer layers blasting outward at thousands of kilometers per second. A supernova. What's left is an expanding shockwave of gas and debris. That wreckage slams into the interstellar medium and lights up. Basically, that's what we call a supernova remnant. The Crab Nebula is the textbook example. Chinese astronomers watched it explode in the year 1054. It was visible in daylight for weeks. Today, nearly 1,000 years later, the remnant is still expanding fast. About 1,500 kilometers per second, a tangled mess of magenta filaments and blue synchrotron light. Supernova remnants are where the universe does its chemistry. Everything heavier than iron was cooked in dying stars. Gold, uranium, the calcium in your bones, the iron in your blood, all blown out by supernovae. Then it drifted through space, mixed into new gas clouds, and got recycled into the next generation of stars. The atoms in your body were, at some point, inside a supernova remnant. That is not a metaphor. Often in the middle of the wreckage, there's something worse. A neutron star spinning hundreds of times per second. A pulsar, or a black hole. The crab has a pulsar at its heart rotating 30 times per second. It's been doing that since William the Conqueror was alive. 5 types: emission, reflection, dark, planetary, remnants. That should be the whole list. It isn't. One category breaks all the rules. Bonus round: the weirdos. Start with molecular clouds. These are basically the biggest structures in the galaxy that aren't galaxies themselves. Giant molecular clouds can be hundreds of light years across and hold enough material to build 1 million suns. They're cold, dense, mostly hydrogen molecules, and this is basically where the entire star formation process starts. Every emission, dark or planetary nebula you'll ever see traces back to a giant molecular cloud upstream. Then Wolf-Rayet Nebulae, a supermassive star right before exploding, blows off its outer layers in violent stellar winds. Not gentle puffs, we're talking winds moving 2,000 kilometers per second, carving glowing bubbles straight into space. The central star is one of the hottest, most luminous objects known, and it's actively self-destructing right now. Wolf-Rayets are basically countdown timers. When they finish shedding those layers, the star goes supernova. That's the ending. Next up, protoplanetary nebulae, and again the name is misleading, nothing to do with planets or protoplanets whatsoever. They're the awkward transition between a dying red giant and a full planetary nebula caught mid-transformation in slow motion. The star has puffed off its shell, but the exposed core isn't hot enough yet to ionize the gas. Once the core crosses 30,000 degrees, ionization kicks in and the nebula essentially switches on like a lamp. And then the ridiculous ones. The Tarantula Nebula sits in the Large Magellanic Cloud, one of our satellite galaxies. It's the biggest, most active stellar nursery in the local universe. Roughly 1,000 light-years across. Absolutely enormous. If Tarantula sat as close as the Orion Nebula, it would cover a quarter of the night sky and cast actual shadows on the ground. Let that sit. A nebula bright enough to cast shadows. Here's the twist. These things are so far away, the light left them thousands, sometimes millions of years ago. The tarantula's light left before humans existed as a species. Think about that for one honest second. Some nebula you photograph tonight have already drifted, dispersed, or been blown apart by newer supernova you'll never see. The image is a fossil. You are essentially looking at cosmic history frozen mid-motion, arriving late to your eyes. So what does any of this actually mean? Nebulae are the recycling system of galaxies. Not poetic, literal. Molecular clouds collapse into stars. Stars fuse hydrogen into heavier elements, then die and blow those elements back out. Some gently as planetary nebulae, some violently as supernova remnants. Those enriched clouds mix, drift, collapse, form new stars. Every atom in your body, heavier than helium, was forged inside a star, delivered to space by a nebula. The Sun and Earth formed 4.6 billion years ago from a cloud seeded by previous dying stars. That cloud collapsed, spun up, flattened into a disk, became our solar system. Before the Sun, everything was nebula. The oxygen you're breathing was inside a red giant. The iron in your blood came from a supernova. You are, chemically, reassembled nebula walking around, watching a video about your own origin story. Here's the kicker though. Some nebulae you can photograph tonight are already gone. The light is en route. The object dispersed centuries ago. Deep space is a delayed message from things that have already moved on. That's every type of nebula. One name, wildly different physics, all one slow cycle. Born, burning out, recycled into the next round. I bluntly explain space every week. Hit subscribe. Next, how stars actually die.